Hi everyone, welcome back to Mathematics 1229A at King's. This video is about section 1.2, which covers dot product, cross product, and applications of those new types of operations. The applications include geometric applications, like finding the area and finding the volume of shapes that are defined by sides given in terms of vectors. In the first section, we learned about a type of multiplication involving vectors called scalar multiplication, where we took a scalar, a constant, like 2 or 3, and multiplied it by a vector. The output of that operation was another vector. We also learned about operations like length, where we take the length of a vector and get a number. Inside this section, we're going to learn about a different type of multiplication that we can do with a vector. So not a scalar multiplication, but the multiplication of a vector with another vector. And there are two different formulations or kinds of multiplication that we'll talk about for vectors, depending on the number of dimensions that we're in. One kind of multiplication is something called a dot product. A dot product can be done as a multiplication between any two vectors that have the same size or have the same dimension. So a 2D vector and a 2D vector can be dot producted. We can take the dot product of them. But for the cross product, the second type of multiplication we're going to talk about, it is specific to vectors in 3D, so vectors with 3 components. The output of the dot product operation is going to be a number, a scalar, and the output of the cross product operation is going to be a new vector. We'll define what the operations are, so how to do it, and then I'll discuss what it means, what the interpretation of each of these operations is. So first, in terms of inputs and outputs. A regular multiplication, so the good old days before vectors entered the picture, the only multiplication you knew about was the multiplication of numbers. A times B is equal to C. 2 times 3 is equal to 6. That was what multiplication was, and it was something you could interpret as a type of addition. That 2 times 3 means you have 3 groups of 2, so 2 plus 2 plus 2, or it could mean you have 2 groups of 3, 3 plus 3. So it was nice, it has simple interpretation, you put in numbers and got numbers out. The newest form of multiplication is a little bit trickier to interpret. We have this vector object, which itself is new and different. We multiply it by a constant and we get a new vector object. So we start with a vector and a number and combine them and create a new vector. For the dot product operation, that's a type of vector multiplication that the input is 2 vectors and the output is a number. And then the last type of multiplication is the cross product operation. It's only an operation that can be done in R3, so only if you're working with 2 vectors that each have 3 components. You put the 2 vectors in, you get another vector out, so a vector that is also in R3, it's also going to have 3 components. And there's a process or a formula or a method that is used to construct these new vectors from the cross products, and a different procedure for dot products. First, the definition of the dot product. I'm going to work here with 2 vectors that have 3 components in them. This operation can be defined for a 2-component vector. Just get rid of the third component and you'll have the correct formula. And later on we'll see that this can be extended easily to higher dimensions as well. It says that if you take the dot product of u and v, what you'll get is the first component of u multiplied by the first component of v plus the second component of u multiplied by the second component of v plus, if it's in 3D, the third component of u multiplied by the third component of v. each of those multiplications, so the u1, v1, u2, v2, and u3, v3, those are standard old-fashioned multiplications of numbers. So each one gives you a number, and then you add the three numbers together, and you get another number. So this whole process gives us a number, even though the two inputs are vectors. So we'll look at a set of examples. The first example here is in 2D. The second example is in 3D. We'll solve or complete both of these calculations. So for the first one, 1, 2, dot, 3, comma, negative 1, we're going to have the first component, 1 multiplied by 3, plus the second components multiplied together, and then we add both pieces together. So plus 2 multiplied by negative 1, and we put the negative 1 in brackets. So we get 3 minus 2, which is 1. So an answer of 1 came out of that operation. On the next side, we're going to do a similar process. We're going to do first times first, so 2 times 3, plus, I guess I should be a little bit careful with the times. That 2 times 3 there, it looks like a dot product. You're not going to like this. I'm going to go back and I'm going to rewrite that first one, because I don't want to use that. I don't want to use the dots anymore for multiplication. I'll use brackets. So 1 times 3 plus 2 times negative 1. Just so there's no confusion about, well, can you take the dot product of two scalars? No, you can't. So 3 minus 2 is 1. Okay, just a different notation for the same answer. Now for the next question, for the 3D vector, we're going to do something similar. We have 2 times 3, so the first times the first, plus negative 1 times 2, so second times second, plus positive 4 times negative 2, and then we can simplify 6 minus 2 minus 8, so that's going to be minus 4. What am I saying? Yeah, minus 4. Notice that the dot product operation can output positive numbers, it can also output negative numbers, and the dot product operation can output 0. We'll interpret dot product in a moment. As a reminder, the first form of multiplication that we learned, it's still a type of multiplication we're going to do. So this is just review from the first lesson. We're given the vectors u, 1, 3, negative 2, and the vector v, 4, 1, 1, and we're asked in part A to find negative 5 times u, and in part B we're asked for u dot v. So negative 5 times u, just like in the first week's lessons, negative 5 times 1, 3, negative 2. So this is a scalar multiplication. The constant multiplies by each piece of the vector. So negative 5 times 1, which is negative 5, negative 5 times 3, which is negative 15, and negative 5 times negative 2, the negatives cancel, we get positive 10. That would be the output, a vector. Now if we do a dot product of u and v, we'll have the first component of u multiplied by the first component of v plus second component of u times second component of v plus third component of u times third component of v. So 4 plus 3 minus 2, which is 5. Again, a number comes out of a dot product, a vector comes out of a scalar product. Based on this definition of the dot product operation, we could prove the following properties. I'm not going to prove them, I'm just going to state them. The first property, it's called the commutative property, is that the order of the dot product does not matter. In other words, u dot v is the same thing as v dot u. You can do an experiment if you want. Go back and redo the examples we just did. Interchange the order of the dot product to interchange the order of those multiplications. So instead of 1 times 4, you have 4 times 1. Still 4. And instead of 3 times 1, you have 1 times 3. Still 3. And instead of negative 2 times 1, you have 1 times negative 2. It's still negative 2. So that property should not come as a surprise. The next property is that if you have a constant multiplied by the dot product of two vectors, you can move that constant around. You could, for example, put that constant with the vector u, and then take the dot product with v. Or you could take that constant and put it with the vector v, multiply it in, and then dot it with u. That second property might look silly, but I'll show you a scenario where you would want to do that. Suppose you have 4 times u dot v, where u is equal to 1/2, 3/2, -1/2, and v is equal to 1, 2, 3. So that's your construction, and we want to compute 4 times u dot v. You could, and actually I make it even worse. I'm going to change it and make it slightly harder. There. You could first do u dot v. Now you're working with fractions, making common denominators and all that stuff. It's smarter to look at the properties you have available that allow you to take that 4 and multiply it into the u first. So I would make the choice based on the particulars, based on the details of the problem. I would make the choice to put the 4 with the u. So 4 multiplied by each of those components. 4 times 1/2 is 2. 4 times 3/2 is 6. 4 times -1 is -4. And then dot that with v. 1, 2, 3. And now we don't have any fractions. So 2 plus 12 minus 12 equals 2. You can compare that to what the process would look like if you first dotted u and v and then multiplied by 4. It's a little bit more work because of that common denominator step you'd have to do. This process can also work in reverse. Maybe you can take a question like this, take the dot product of 10, 20, 30 with 5, 8, 9, and think of a way to simplify that. It's not that bad because it's tens. Well, you know what? I'm going to do the same thing I did in the last one. I'm going to make it worse. I'm going to put 27, 9, 81. What you should do is you should factor a 9 out of that first vector. So you'd have 9 bracket 3, 1, 9. Then do the dot product of the 3, 1, 9 with 5, 8, 9. Then multiply by 9. So your operations are going to be slightly simpler that way. Anyway, I'm going to erase that because it's not typically something that we do, but you might do the step that's shown above. The next property is called the distributive property, which says if you're taking the dot product of u, of one vector, which we'll call u, with the sum of two other vectors, which we'll call v and w, you can distribute that dot product into u dot v plus u dot w. So you can do two different dot products and add the results together. This is another type of operation that can run in both directions. You may start with u dot v plus u dot w and say, wait a second, I can factor the u dot product out. I could write it as u dot v plus w. So just add v and w together, create a new vector, and now you only have a single dot product. So fewer multiplications will be needed. Okay, next property. This one should be fairly obvious. If you do an experiment, u dot 0 is equal to 0 as long as that 0 vector has the same number of dimensions as u. By the way, if it has different dimensions, if you ever take two vectors that don't have the same number of components and do the dot product, that operation is undefined. They have to have the same number of components. Same as vector addition. Okay, next property is that if you take the dot product of a vector with itself, you'll get the length of the vector all squared. You can prove this if you want. So I'll call it optional homework, but show that this is true for any vector equals a comma b. It's not hard. This is not difficult to do. So show that if you have components A and B, which are very general, that can be any numbers, that this property is true, independent of what those numbers are. Oh, I should have mentioned this. A good thing that that little arrow is there to remind me. Notice that in the fourth property, that we have the dot product of a vector with a vector, and the output is a number. So the dot product between the vector u and the zero vector is the zero number. Okay. First question that tests those properties directly. We're told that u dot u is equal to 16. And based only on that information and no other information about the vector u, we're asked to find the length of u. This can be answered in the following way. We know that u dot u is equal to the length of u all squared. That's one of the properties on the previous slide. Thus, I'm going to replace the u dot u with the magnitude of u squared, or length of u, not magnitude, length of u squared equals 16. Try to keep the language consistent. Length, norm, magnitude. Okay, so that's what we know. So if something squared is equal to 16, I'm going to take the square root of both sides. That means the length of u is plus or minus 4. I'll put a question mark there. And something's wrong with that answer, because length is always positive. Length must be positive. So the length of u is equal to 4. Only 4, not plus 4 and minus 4. Okay, now the interpretation. What is this dot product telling us? So here I have drawn two vectors, u and v. U appears to be 1, 4. V appears to be, oh, it's not very nice. Maybe 3.5, 2.5. So not very nice numbers, but they're not meant to be nice. In between these two vectors, as long as they're not parallel vectors, as long as they're not collinear vectors, there will be a non-zero angle between those vectors. There's actually two angles between them. There's a small angle that's drawn here and the big angle that goes all the way around. When we talk about the angle between two vectors, we will always talk about the small angle, the smallest angle. One thing to note is that this smallest angle will always be under 180 degrees, also referred to as pi radians, if you're used to working in radians. We're going to use the symbol theta for angles. So that's the symbol that's in between the u and the v vectors. When you look at a picture like this, you may think you have to go back and review your trigonometry from high school, and you don't. We're going to have something that looks like trigonometry in the course. We're going to have like the cosine function, but we're not going to do anything with it. We're just going to have a formula that has it. You're not going to have to go back and think about SOHCAHTOA and those types of things. Although it is helpful to connect what we're doing inside this class to what you learned inside previous classes involving geometry. Okay, and here's the connection between u, v, theta, and the dot product between u and v. So here's the geometric connection and kind of one of the interpretations we can have for dot products. It's going to be the case that for any vectors u and v, whether you're in 2D or you're in 3D, that the dot product between u and v is going to be equal to the length of u multiplied by the length of v multiplied by the cosine of the angle between u and v. This is a tougher one to prove without without spending more time. And I don't want to spend more time on it. I'll just allow this to be treated as a definition. Now, following from this, just from basic rearranging, so I'll show you what the step essentially is. If you have let's say 20 is equal to 5x, how do you solve for x? Well, you divide both sides by 5. X is equal to 20 divided by 5. Following that type of operation, we can rearrange the expression for u dot v to isolate for cos theta. What we'll do is we'll divide both sides by the length of u, and we'll divide both sides by the length of v. So we'll just bring them underneath the dot product. Thus, cos theta is equal to u dot v divided by the length of u and the length of v. So with a dot product and with the length of u and the length of v, we can construct what the angle between u and v is. Let's do one example and then we'll cut to the next video. Find the value of cos theta, where theta is the angle between u and v, if u is equal to 3, 4 and v is equal to 2, -1. So definition, you can start with this formula that u dot v is equal to length of u times the length of v times the cosine of theta, or if you want, you can start directly with the cos of theta expression. Cos of theta is equal to u dot v divided by length of u times length of v. So it doesn't matter which way you go. I'm going to start with the second one. So cos of theta equals u dot v, so I'll put those in, 3, 4 dot 2, -1, all divided by the square root of 3 squared plus 4 squared, and the square root of 2 squared plus -1 squared. So those are the two length calculations in the denominator and the dot product operation in the numerator. Okay, now let's simplify. So 3 times 2, 6, 4 times -1, -4, and then in the denominator we have the square root of 9 plus 16 multiplied by the square root of 4 plus 1. You can simplify 2 over the root of 25 times the root of 5, which is 2 divided by 5 times the square root of 5. In some math classes, you'd spend time rationalizing, like bringing that root 5 up, but we won't do that. The answer would look like this. So I'll stop here. In the next video, we'll do more examples of dot products.